Alrighty, part 2 of section 3.8. This is going to be entirely devoted to something called logarithmic differentiation. Really long, fancy sounding name. But what it is, it's using logarithms to make problems easier so that you can then find the derivative. And the best way to do this is just to show you what in the world we're talking about here and how that's going to apply to the questions. Alright, so this is actually number 48 on page 178. So this is one that you're inside of your your homework area there. So this is the function that we're talking about in this example. Alright, so that thing right there, if we're supposed to take the derivative of that, first of all it's a chain rule. Now the top's a 1, so that helps, but the bottom is a triple product. The only way to make that doable is to FOIL that out, which really wouldn't be too awful. I mean, this one isn't as bad as some of them, but excuse me. But still, that's not going to be a whole lot of fun, and there's a lot of places to go wrong. So we can use logarithms to kind of tear that thing apart a little bit because you've got your logarithm laws at your disposal. So what I'm going to do is I'm going to take the natural log of both sides. This is what logarithmic differentiation is, kind of a two-part process. First of all, you have to take the logarithm of both sides of your equation or of whatever you do. It's kind of like the implicit differentiation in that respect. You do everything, both sides. Now this here, then sorry, the thing on the left is going to be fine. The thing on the right I can then tear apart. Now natural logs, logarithms, if you are dividing natural logs, that means subtract. So I'm going to do natural log of 1 minus the bottom. Now the bottom is three things multiplied together, and multiply means add. So that means I can treat that as three tiny separate logarithm pieces, like so. And that doesn't exactly look easy, but each of those individual, there's four small little derivatives. Each one of them is much easier than the whole to start with. So sorry, still coughing from the last video. Wow. Anyway, okay, so I'm going to take this negative sign and I'm going to distribute that through at the same time that I'm doing my derivatives, because I'm about out of room here at the bottom, but those are just going to all be negatives. So on the left side, the natural log of y, that's 1 over y dy, or I think actually your book writes it as y prime. And that's what we're going to find. That's the implicit differentiation part of it. It's lagging a little bit there. There it is. The implicit differentiation thing, part of this comes out when you're taking the derivative with respect to y, so we're going to have a y prime because we took the derivative of a y. Then we do on the right side the derivative of natural log of 1. The natural log of 1 has a value of 0, so the derivative of that's going to be 0. Of course, that just disappears. And then the rest of this, the derivative of natural log of t would be 1 over t, and that's going to be negative because of the negative sign. The derivative of natural log t plus 1 would be 1 over t plus 1, and then the negative. Each one of these is times the derivative of the inside part of that, the u. And the derivative of t plus 1 is 1 again. And then the derivative of natural log t plus 2 would be 1 over t plus 2, times 1 again with the negative out in front. So this right here is my kind of my first and second stages, I suppose. This is the logarithmic differentiation part of it, I guess. We took the logarithm of both sides and we broke it apart so that it had easier pieces with which to deal there. And then we took the derivative of it. And so now we're sitting there with this y prime down here in the bottom left-hand corner, and we want to get that by itself. So I'm going to erase everything at the top and leave that at the bottom. And then I'll show you what to do with it from there. Okay. There it is. Okay, so first of all, you see you got a y, 1 over y, so that's the y variable. Now that y is the original problem. 1 over t plus 1, t plus 2. That was the original y equals equation. So I'm going to actually multiply everything by the y down here. I'm going to multiply both sides by y to get this y to cancel with this y. And then all I'll have left is the y prime. So that's going to be my parenthesis piece there. Like so. Let me get rid of this. And then times my original y, this thing, which I'm going to write as the function. There we go. Okay, so that hideous, horrible, horrible mess, this one really doesn't help us out a lot as far as did we make it any easier? Probably not really, but it's a good example of kind of all the little things that you can do. The reason this is not working out well is because it was a quotient rule that had a triple product rule embedded in it, so that's why the mess. Anyway, now from here you'd have to decide what you needed to do. If you were trying to solve this, you'd have to do a common denominator with this jazz, and then simplify the fraction multiplied by that one on the right. You could maybe get away with just leaving it right here if you were being done, but we're going to put it together because odds are if we're going to this much trouble, we must have a point, so there must be a goal or a reason to solve this. So I have some intermediate steps. I'm not going to do every single one of these because you could do the arithmetic here, but you need to find a common denominator of that thing which has the left bar, the orange bar underneath it, and that would be, let me see here, find my stuff. I got this written out so I don't have to make a mistake with you guys all watching me. So this is what the denominator, this is what that piece on the left would end up being. And it's again, it's just a common denominator. Nothing fancy. Oops. Not that. These T's look an awful lot like parentheses. Don't like that very much. All right, so if I do a common denominator, it's going to be each separate piece, t times t plus 1 times t plus 2, because your denominators here are all three separate, so it's really the only thing you can do. And if you look close, you'll see those top pieces are what was missing from the denominators. Now I removed the negative sign out of there because instead of making all of that junk negative, I'm just going to move the negative sign over to the right. I'm going to change this thing to a -1. And that's okay because all of these pieces are negative to begin with. I'm just going to transfer that sign over there. It's kind of like factoring. And then my denominator is this over here. All right, so now I'm multiplying, and I would have to simplify that the top of the fraction on the left. I have to simplify this thing right there all the way out and see what I could cancel. When I got done with that, the answer would be this. Or at least this is one version of the answer. You could very easily have something similar that wasn't exactly the same. There it is. All right. So you just have to try this same thing. It's kind of like the other natural log derivatives. There's so many possibilities. You just got to give it a try. But the main thing is when you're looking at a function that is really complex, you can use natural logarithms to bust it up a little bit and make at least parts of it easier. That way you can avoid these ugly quotient rule with triple chain rules, or you can avoid our triple product rule that we just had here, or you could have two chain rules in a row embedded inside of a quotient rule, and you can split all those things apart and use the three logarithm rules to kind of make that easier for you. So give that a try. Same thing. It's a lot of algebra, lots of places to go wrong. So take your time, go slow, and let me know if I can help you.